So my name is Jianliang Wu. Today I'm very glad to share our work on persistent low energy. This is a joint work with my colleagues at Purdue University and at the University of Florida. So first question someone may ask is, why do we care about persistent low energy? The answer is simple, because it's everywhere. So it's almost enabled in every smartphones, and it's widely used in the Airbus. And it's also widely used in the privacy-sensitive scenarios like location tracking and contact tracing during the COVID-19 pandemic. BOE itself has also provided privacy protection mechanism like the MAC address randomization mechanism. However, existing research on BOE privacy focuses on only one slice of BOE, and a systematic study is still missing. So in our work, we aim to provide a systematic study of BOE in terms of traceability or untraceability. So to begin with, we need to define what is untraceability in BOE. And after that, we abstract and model all the possible 5 communications in the BOE. And lastly, we utilize form verification tools like ProVerif to exhaustively reason about all the communication scenarios and to find if there are attacks, possible attacks that can be exploited by attackers to track a device. So we define the traceability of BOE based on protocol level identifiers. And we first categorize the BOE messages into 2 types. The first is linked messages. If a message contains a unique identifier or some field of this message can be derived from this identifier, we categorize that as linked messages. And the rest of the messages are irrelevant messages. And based on these 2 types of messages, we summarize 2 types of device tracking. One is passive tracking, meaning that a tracker can passively observe the linked messages that can be linked to a unique identifier. And the second is active tracking, meaning that a tracker can either send out linked messages that can be related to a unique identifier and receive the response of either linked messages or irrelevant messages. Or the tracker can probe with a irrelevant message and receive a linked message that can be related to a unique identifier. And then the untraceability, if a device is untraceable, meaning that none of these 2 tracking is possible. So after that, we abstract all 5 possible communication scenarios in BOE and model them. These 5 communication scenarios are pairing, scanning, communication establishment, encrypted communication, and authenticated communication. And the transition between these 5 communication scenarios is shown in this figure, and we build a model based on this. And lastly, we utilize the form verification tools to reason about this untraceability property. So one of the challenges we have here is how to define how to model the untraceability property. Some of the existing work use the Diff-Equivalence, which is used to model a privacy property in formal analysis. However, it may introduce false attacks. So in our work, to avoid false attacks, we model all the trackers' behaviors, including the passive and active trackers based on the unique identifiers. And then we'll propose an event-based representation for the untraceability. For example, in the passive tracking scenario, the untraceability property can be represented like this. So in the model, when the devices send out a linked message, it emits an event, Alice send event. And if the tracker can observe this event, the model emits an event tracker receive. If these two events happen at the same time, meaning that the tracker can observe this linked message from the device and thus can check the device. So with this, we can find the attacks without introducing any false attacks. So in total, we have verified 152 properties and found 44 violations caused by 4 issues that can lead to 8 different attacks. These 4 issues are one IRK reuse. IRK is an identity resolving key, which is used to generate the randomized MAC address for Bluetooth Low Energy. And second is Bluetooth address reuse. This Bluetooth address is the MAC address for Bluetooth Classic, which is unique and cannot be changed. Third one is CSRK reuse. CSRK is a data signing key. And the last one is the identity address reuse. This identity address is a MAC address of the Bluetooth Low Energy. So we also investigated 13 different implementations on mainstream platforms, including Android, iOS, Windows, and Linux. So we found that all devices are affected by at least 2 issues, and actually 12 out of these 13 implementations are affected by 3 issues. And we reported all issues to the related vendors, and Google confirmed all of our reports are confirmed, and Google rated 2 of the issues as high severity. And then let's see some exciting demos. So this demo shows that a device, how a device can be checked if it enables the COVID-19 contact tracing system. So the first step is this device the user pairs the phone with a device under the attacker's control. For example, when she moves into an Airbnb apartment, she pairs her phone with a smart lock. And later, the lock may be compromised by the attacker. And during pairing, the key is distributed to the smart lock. And when the user leaves, she unpairs her phone with the smart lock. But this key remains valid after unpairing. And then in step 3, the tracker can utilize the IR key to resolve the MAC address generated by the phone, and thus can identify this phone and check it. Because when the contact tracing notification enables, the phone actively broadcasts advertising messages, and only within a very close range to the phone, the tracker can receive such messages. So this is another case study showing that device can be checked as long as the phone has the Bluetooth functionality enabled, even without running any Bluetooth services in the background. So the first 2 steps are the same. The user pairs the phone with a device under the text control and then unpairs with it. During pairing, even though only the low energy is used, but the MAC address of the Bluetooth Classic is still distributed to the peer device. And thus, the tracker can utilize that, the MAC address of Bluetooth Classic to check the device by actively sending out probing messages, the message, the request to establish a connection with the device. So no matter if connection establishment or a connection reject is received, the attacker knows that the device is close to their tracker. And if there's nothing received, for example, timeout, then probably the Bluetooth is either turned off or the victim device is too far away from the tracker. So this is a shortened demo video, and we have the 4 demo video in our repository. So to sum up, we conducted a systematic study of BOE traceability, and we find 4 issues that can lead to 8 different attacks. And we have our models publicly available, and our demo videos are also available in our repository. And thank you for your attention, and I'm glad to take any questions. Thank you.